Hello and welcome you all to the 9th lecture of electroweak interactions in the standard model of particle physics. And today we are going to actually take up the Dirac equation solution with a gory detail, and we are going to actually solve this Dirac equation for p not equal to 0. You remember in the previous class we did it for the static cases, but today we are going to deal it with the full solution, and then it is going to reveal something very interesting for us. So that is going to help us in tackling the interpretation of all the fermions that we are going to handle in the standard model of particle physics as we go along. Okay, so let's get started. So you all remember what was the Dirac equation. So the Dirac equation was essentially I gamma mu del mu minus m psi x t equal to 0, right? And here gamma mu is the Dirac matrix, and psi is essentially what we call the Dirac spinor. And so basically it's a equation which is like almost like a wave equation. So the solution will be also like a wave solution. So the part which has this the phase space is essentially e to the power I p dot x minus e t as very standard, and the part which we also understood that the Dirac equation need to have spinors, which are the 4 component column matrices. That spinorial part is essentially embedded in this UEP. So the test solution for the Dirac equation, which we actually did take also in the yesterday's class, is essentially this following form, that psi x t is equal to UEP e to the power I p dot x minus e t, and I remind you that the spinorial part is essentially embedded in UEP. Okay, now if we put it back into the Dirac equation and try to find out how exactly UEP solves this equation for this one. So what exactly we get? We did the algebra in details, and you can remind yourself or go back to your previous calculation to show that this is going to come like gamma mu p mu minus m UEP equal to 0. So there is a shorthand notation which we often write, which is like p slash minus m UEP is equal to 0, where we write this p slash is nothing but gamma mu p mu, because you see this Lorentz index gets contracted. So however, this still is a matrix, right? So therefore that is there, but this is a p slash minus m UEP equal to 0. So this is the equation that the UEP needs to solve, right? And we did the solution for p equal to 0 case. Now let's look into the possibility when p is not equal to 0, correct? Now you remember what was p mu. P mu has essentially 4 components. The first component is energy, the last 3 components are the momenta, and in quantum mechanics these are operators. E is I del del t and p is minus I del. Okay, all right. But now let's come back to this equation. Gamma mu p mu minus m e u e p equal to 0. यहाँ से क्या आएगा? No, so we get, if we inflate it, this will have E gamma 0 minus Px gamma 1 minus Py gamma 2 minus Pz gamma 3 minus m UEP equal to 0, right, with p not equal to 0. Now we can also use the matrix forms in the Dirac-Pauli representation, which we already derived, or rather pointed out in the previous lectures, that gamma 0 will be 1 0 0 minus I, gamma I will be 0 sigma I minus sigma I 0, and the sigma i's are the Pauli spin matrices, right? So now if we explicitly put it here, how exactly this equation looks like? So from here to here we can see that this will be like I 0 0 minus I into E minus 0 sigma dot p minus sigma dot p 0 minus m I 0 0 I UEP is equal to 0. So this is exactly how the Dirac equation now looks like if you put explicitly the gamma 0 and gamma i's here, correct? All right. So now I would like to also find out what is sigma dot p. Now you remember that the Pauli spin matrices are as follows: sigma 1 is 0 1 1 0, sigma 2 is 0 minus I 0, and sigma 3 is 1 0 0 minus 1. So, let us then try to find what is sigma dot p. So, you can completely see that the diagonal entry will be with sigma 3, that means with pz, and what will be the other diagonal component? This will be minus pz. What will be here in this first off diagonal component? This will be px minus I py, right, because you have sigma 1 having 1 here and sigma 2 having minus I here, and on this entry we will have px plus I py. Once again you have 1 from sigma 1 and I from sigma 2, right. So, this is what the sigma dot p looks like. Now, what is UEP? Now, UEP is a 4 component Dirac spinor, as we said, and what we can do, that we can rewrite it in terms of two component spinors, which are also sometimes called while spinors. So, let us call them UA and UB. Okay. So, what we are writing here, that we are writing that suppose UEP is constituted of two component spinors. Let us call them UA and UB, where UA looks something like this, it has 2 entries, and UB also looks something like this with 2 entries, and as I said that these are sometimes called while spinors. Okay. So, the Dirac spinor is the 4 component one and the while are the 2 components ones. Okay. Now, with this, if I just put it back in the Dirac equation, how exactly it looks like. So, from this equation you see that the form is E minus m. So, the diagonal entry is E minus m into I. So, this I is essentially a 2 cross 2 identity matrix minus sigma dot p, and on this side you have sigma dot p, and on this entry you have minus of E plus m I, and that acting on UA UB, which is actually the UEP, is equal to 0. So, this is how exactly we can rewrite the Dirac equation from this above one. Okay. Now, let us try to do the matrix multiplication. This is very straightforward. E minus m I into UA minus sigma dot p UB equal to 0, and sigma dot p UA minus E plus m I UB equal to 0. So, these are the 2 equations that we have actually after doing the matrix multiplication. Now, from the first equation what we get, I can also rewrite that UA is equal to sigma dot p by E minus m into UB. On the other hand, from the second equation what we get UB equal to sigma dot p by E plus m into UA. Okay. Now, what I am going to do, so this basically means that if I have some way of understanding or knowing what is my UA, I can find UB, or if I have some hunch of knowing some values of UB, I can find UA, which will solve the Dirac equation according to the following rules, right. So, let us inflate this second equation once more, and where UB is sigma dot p by E plus m into UA. So, let us see how we can rewrite this quantity. Now, this is 1 by E plus m, this is just a number, it comes out, and what was sigma dot p? You remember that sigma dot p we found out here, and this is pz px minus I py px plus I py minus pz into UA. So, therefore, what we have done here, that we have expressed UB in terms of UA and sigma dot p with this 1 by E plus m. So, now what we can do, that we can choose the simplest orthogonal choices for UA. Now, what can be the simplest orthogonal choices for UA? This is something that we can very well understand, that there are 2 possible choices that we can do. One is, these are 2 component spinors, right. So, therefore, we can do it like 1 0, or we can choose 0, 1. Correct? So, these are the two possible choices. So, suppose if I choose u a equal to 1, 0, then can I write what exactly is the form of suppose u b, right? I say that yes, we can do that. This is simply u b equal to 1 by e plus m p z p x minus I p y p x plus I p y minus p z multiplying with 1 0, and that is trivial, right. So, this will be simply p z p z, and then this will be p x plus I p y, as simple as that. So, then for a choice of u a which is 1 0, I have a u b which actually will satisfy the Dirac equation, and that will be 1 by e plus m p z p x plus I p y in the column, right. So, therefore, we are now in a position to write the full Dirac matrix, right. So, let us call that to be u 1 e p, and that will be u a u b arranged in the vertical columns, and u a is what? U a we have chosen to be 1 0, and what was u b? U b is p z by e plus m, and the last component is p x plus I p y by e plus m. Excellent. So, we have the full matrix from here. Now, let us try to see what is the limit of this spinor, that is a solution of the Dirac equation that we have obtained for p not equal to 0 case. What happens when we take the p tending to 0 limit? It is pretty obvious that this solution is going to be 1 0 0 0, right. So, this is one solution which is actually giving you, this is the one that we obtained, which actually gives you the solution of E is equal to plus m in the massless in the rest frame, right. Therefore, this is the one which actually correspond to this choice 1 0 0 0. Okay. And also you observe that I have chosen a normalization which I have called n1, which I have not determined so far, but you are going to determine it in your tutorial exercises. Now, let us choose the other possible combination of orthogonal combination of u a, which is to choose 0 1, and for that u b will be once again following the same relation 1 by e plus m p z p x minus I p y p x plus I p y minus p z multiplying with 0 1, and can we do the matrix multiplication quickly here? This will be p x minus I p y, right, and this will be minus p z. So, can we then write the full u2 Dirac solution, which is now for a different choice of u a, which is 0 1. So, let us try to write that. So, this is 0 1, and this is p x minus I p y by e plus m, and then I have minus p z by e plus m. Once again, I am interested to match or go back to the rest frame solution or the rest particle solution when p tending to 0. Can I do that? And the answer is yes, I can do it very well. And in this particular case, what exactly the solution is going to look like? This is going to look like 0 1 0 0. Now, this is also the solution that we actually obtained, which gives you, positive energy solution with E is equal to plus m. So, these two solutions, so to say, which we have obtained so far, u1 and u2, these are the particle like solutions, which gives you positive energy particles, right, positive energy solutions. So, however, this must be stated that these two solutions that we are we have obtained u1 and u2, these are subject to the choice of two orthogonal forms of ua, which are anyway arbitrary. So, any other orthogonal form is equally valid, since you can always write any solution as a combination of u1 and u2. So, the specific form of ua is basically saying that we are choosing a basis, and this basis is usually referred or labeled along the z axis, the one that we have done. Now, so these are the two solutions, but we know there exist 4 solutions. Now, what we can do, that now we can say, okay, we had 2 possible orthogonal solutions for ua, and for that we could find what are the corresponding ub, and we found the corresponding Dirac matrices essentially, which will solve the Dirac equation. Now, the question is, what are the other 2 solutions? Now, we also know that we can express ua in terms of ub. So, we can choose 2 different orthogonal forms of ub and find those corresponding ua's from this relation, because you remember we had 2 relations, like ua was related to sigma dot p by e minus m into ub. So, we can exploit this relation and use the 2 orthogonal forms of ub and find the corresponding ua and find the other 2 solutions of the Dirac equation. So, let us do that. So, the other 2 forms, so ub you can once again choose 1 0 and 0 1, and we are going to substitute it here in this particular equation. ua is equal to sigma dot p by e minus m into ub. Okay. So, if you do that, once again we are using the sigma dot p, which is pz px minus ipy px plus ipy minus pz into ub, and let us put this ub equal to 1 0 for the primarily, and for that ua is going to be just the matrix multiplication of this, and let us try to do this calculation very quickly and see what exactly it provides. So, this is going to give you pz and then px plus ipy, correct. So, now if I want to write the full Dirac solution, how exactly it will look like? It will look like that now you remember that first we have to write ua and then ub. So, this will be pz by e minus m and then px plus I p y by e minus m, and this was for the choice of u b with 1 0. Now, once again I am interested in looking into the p tending to 0 limit of this solution. So, it is pretty obvious that this is going to give you 0 0 1 0, and it is very easy for us to remind ourselves that this is one case for which we actually get a negative energy solution, E minus m kind of a solution, right. So, this is going to give us negative energy solution. All right. Now, let us take the other orthogonal combination and get the other solution. Okay. So, the other orthogonal combination for ub will be 0 1, and let us do this matrix multiplication. So, this is pz px minus I py, and this is px plus I py minus pz 0 1. And if you do this matrix multiplication, this is going to be px minus I py, right, and px minus I py, and then this will be minus of pz, correct. So, the full spinor, let us call that u4, that will be what? This will be px minus I py by e minus m minus pz by e minus m, and this is 0 and 1 for the ub. So, what is the p tending to 0 limit that we get actually from this one? Well, this is also very obvious. We are going to get 0 0 0, 1, and it is easy to check or remind ourselves that this is going to give us E is equal to minus m, once again negative energy solution. And this is something that we have already envisaged, that in Dirac equations, or rather in any relativistic quantum mechanics, this is something which is unavoidable. We are going to get the negative energy solutions, and the interpretation that we have done is essentially that these are nothing but the antiparticles. So, yeah, once again, this is to reiterate that if we choose p tending to 0 limit, U1 U2 solution produces the E greater than 0 spinors, whereas U3 U4 solution reduces to E less than 0 spinors at rest, that we actually found out. Okay. So, now the point is, you can also check this. This is something which I am not going to work it out in details, that whenever you choose any of these spinors U1, U2, U3 and U4, put it back in the Dirac equation, you are actually going to retrieve this relativistic energy momentum relation E square is equal to P square plus M square. Now, this is something that you can easily check, at least for U1. I will give just a hint and what you are going to do. So, you write the Dirac equation in this particular form in explicit. So, this is the form that we are referring to. This is the form E minus m into I, which is a 2 cross 2 matrix, minus sigma dot p minus E plus m I acting on U A U B. Now, let us choose the U1 solution. So, the U1 solution kya tha? U1 solution was actually of this particular form, right, 1 0 Pz by E plus m, Px plus Ipy E plus m. Okay. So, let us choose that kind of solution. So, this is 1 0 Px plus Ipy by E plus m and then Pz by E plus m. What I am going to do, or rather you are going to do, you simply do a matrix multiplication. What I have done, that I have explicitly written that E minus m into I, so which is E minus m 0, 0 E minus m, once you multiply with a 2 cross 2 identity matrix, and I have explicitly written the minus sigma dot p, which we all written above. So, this is something which I have explicitly written, and then I have a 4 cross 4 matrix on this side, which will be acting on this U1 EP to 4 component spinor, and then you do matrix multiplication and do this algebra to show that you essentially adhere to E square is equal to P square plus M square. So, this is in a way to validate that the solutions that we are actually getting is making complete sense, right. And you can also see that therefore, this is still not unavoidable, that you have the positive energy solutions coming in the form of E equal to plus square root of P square plus M square, which are associated with this U1 and U2 solutions that we obtained, and on the other hand U3 and U4 can be associated with the negative energy solutions of E is equal to minus square root of P square plus M square. So, therefore, what we interpret is that although the Dirac equation was primarily written in order to avoid the antiparticle or negative energy solutions, but this is unavoidable, right. So, the 4 different solutions correspond to 2 E greater than 0 and 2 negative energy solutions, and these negative energy solutions refer to what we call the antiparticles. Now, the point is that theoretically this was interpreted by Feynman and Stueckelberg that this must be corresponding to antiparticle solution, but unless in physics there is an experimental discovery, we do not trust any of these theoretical statements. And it turns out that in 1932, David Anderson in Caltech, they actually discovered positron in the cloud chamber with magnetic field, which actually bends the charge particle coming from cosmic rays, and it shows the traces of particle which has the same E by m ratio. So, it has all the properties very similar to that of electron, but the bending occurs in opposite direction, that means it must possess a opposite electromagnetic charge, and this is interpreted of what we call the positron or the antiparticle of electron. And this was, of course, given a Nobel Prize in 1936. And so this was a pioneering thing that could happen, that Dirac solution on one side predicted that you have antiparticle solutions or negative energy solutions, and those antiparticles are actually something which is really seen or physically realized in nature. Now, this is something that we have already discussed before, that what was the Feynman-Stueckelberg interpretation of negative energy solution to be associated to antiparticles. You basically say that the negative energy solutions which are moving backward in time, you can associate them to positive energy solutions moving forward in time. So, here I give you a schematic of an explanation of E plus E minus annihilating to photon, although this photon has to be a virtual one, that is a different story. But let us for the time being think of a possibility like you have an electron which is actually coming with an energy E greater than 0, okay, and it emits a photon with energy 2E, say for example. Okay. So, therefore, it produces another electron, say for example, with energy minus E. Of course, from the energy conservation you actually have that, and suppose this is the way that you actually express this diagram, and this is the case where you are actually seeing a negative energy electron to be produced in this experiment. Now, you can say that this is an equivalence of saying that you actually have a positive energy antiparticle which is actually annihilating with the particle electron. So, instead of saying that this electron is coming and going like this, which conserves the electromagnetic charge, you can also say that this electron is getting annihilated with a positron, with an opposite, to produce a chargeless particle which is a photon. So, you can also interpret that, okay, I can have an electron with energy E greater than 0 and a positron with energy E greater than 0, once again moving forward in time to produce a photon with energy 2E, and that conserves everything, right. So, you can very well have a positive energy positron with energy E annihilating with a negative energy or positive energy electron to produce a photon with 2E. Now, the point is that, so therefore, I can very well have an antiparticle solution also. So, the U3 and U4 that we actually obtained previously, which gives me this negative energy solutions, these are basically propagating backward, and these are the what to say is the antiparticle solution. But it is more convenient that instead of having this negative energy, negative momentum particles propagating backward in time, in order to replace that to positive energy antiparticle like solutions, and this is precisely the prescription by which we can actually find the antiparticle solutions of the Dirac equation also. So, what we can say that we can do this, that we can express, I mean without going further details, let me express that instead of writing the solution like u e p into e to the power minus e to the power I p dot x minus e t, if I write the solution to be psi x t is equal to v e p into e to the power minus of I p dot x minus e t, then essentially this corresponds to a antiparticle solution, and this spinor V e p will basically be the antiparticle spinor. So, the way that we actually obtained 4 particleized solutions with 2 positive energy and 2 negative energy solutions, we can actually obtain 4 antiparticle solution using this template solution, and with which we will find out 4 antiparticle solutions, that also with 2 positive energy and 2 negative energy. And usually the standard way of doing it is that I will choose 2 positive particle like solutions and 2 positive antiparticle solutions, and that will give me a full set of expressions. So, this is basically the standard. So, the equivalence is, once again let me remind you that essentially we say that U4 of E minus P into e to the power I of minus p dot x minus of minus E t, this negative energy and negative momentum solution has been identified with V1 of E comma P with e to the power minus I P dot x minus E t. Now, so this is this thing. So, this is you can do not only for U4 and U3, but in general, as I said, that with a form like psi x t is equal to V of E p e to the power minus I P dot x minus E t. So, with this today we are going to stop, and we are going to come back to the identification of spins that we actually did, and we will point out that there are some issues in identifying the spin. Rather, it will be important to define something called helicity, but for that we have to stay tuned and come for the next class. Okay, thank you.